Welcome to the Two Beans in a Pod.
Today, we are deep diving into a headline that, honestly, it sounded like the start of a disaster movie. We're talking about the powerful X1.9 solar flare that just erupted on December 1st, 2025.
Yeah, when you see X-class in the news, you know it's the real deal. It's like the highest category there is.
It's the top of the scale. And X1 is already a colossal release of energy.
And we're talking about an X1.9, so that's right on the edge of being an X2. It's like a major league earthquake, but, on the sun's surface.
Exactly. It's a huge, sustained burst of power. And it tells us that solar cycle 25 is really ramping up, getting close to its maximum intensity.
Right. It feels like the sun is getting, angry.
It's definitely getting more volatile.
Yeah.
And I think for you, the listener, the big question is, okay, if this thing was so powerful, why are we all just going about our day? Why didn't the lights flicker?
Why isn't the internet down?
Precisely. And that's the mission of our deep dive today. We need to unpack the difference between what did happen, the immediate effects, and the much bigger catastrophe that we managed to avoid.
And it was all thanks to a bit of cosmic geography, right?
That's the key. So let's start with that initial shock, the instantaneous part. What is a solar flare, really?
It's not a physical thing hitting us like a solar wind. It's energy.
It's pure energy, a sudden, incredibly intense burst of electromagnetic radiation. We're talking high-energy X-rays, extreme ultraviolet light. It's all released when these tangled magnetic field lines near sunspots just snap.
And the critical thing here is speed. It's radiation.
So it's traveling at the speed of light.
Meaning if we see it erupting from the sun, the effects are already hitting our planet just seconds later. There's no warning time.
Not at all. This X1.9 flare, it peaked at 0249 Coordinated Universal Time. And at that exact moment, that flashbulb went off, and it immediately slammed into our planet's atmosphere on the sunlit side.
Okay, so we know it hit us instantly. What was the actual measurable consequence here on Earth?
It triggered what NOAA calls an R3 radio blackout. That's strong on their R scale.
The radio blackout scale.
Right. And that scale, it just measures the effect of that immediate X-ray shock wave. And R3 was pretty much unavoidable with a flare this big.
Okay, let's break that down. What does an R3 blackout mean for someone, say, a pilot flying a plane over the Pacific or a ship captain? What do they actually experience?
They lost their long-distance sight and voice. It's a critical failure for high-frequency radio communications, HF radio.
That's the 3 to 30 megahertz band, right? Used for long-haul stuff.
That's the one. It's crucial for aviation, for maritime traffic, for the military, because it relies on our atmosphere acting like a giant mirror.
Walk us through that mechanism. How does the sun, break that mirror?
Well, think of our ionosphere in layers. You've got the lower, denser D layer, about 80 kilometers up, and higher, less dense layers above it. Normally, those HF radio waves, they're strong enough to just punch right through that D layer and then bounce off the higher, clearer F layer. That's the mirror. The signal comes back down to Earth hundreds of miles away.
So the F layer is the mirror. Got it.
Exactly. But when an X-ray flare hits, it dumps a massive amount of energy into that lower, dense D layer. The D layer becomes intensely ionized. It's just suddenly packed with all these new electrons. So instead of the radio waves passing through to the mirror...
They hit that charged up layer first? So the D layer turns into a sponge instead of a window.
That's a perfect way to put it. It becomes a sponge. It just absorbs the radio waves. The signal loses all its energy right there.
Wow. And an R3 level means that happened pretty much across the entire sunlit side of the Earth.
Widespread loss of communication. And given the timing, 0249 UTC, the affected area was the Australasian sector. So for a few minutes, critical HF comms across Australia and parts of Southeast Asia were just gone.
So if you're a pilot crossing the Indian Ocean, your main long-range radio just goes silent. You'd have to switch to other systems like satellite comms. That's a real tangible failure, even if it's brief.
It's very acute. It's fast. But here's the massive distinction. This is the part that saved us from a systemic global crisis.
This is where we get to why it wasn't a bigger disaster. The decoupling.
Right. It all comes down to location, location, location on the sun.
Okay.
This X1.9 flare, it came from a new active region, later called AR4 to 299, and it was positioned right near the solar northeast limb.
The very edge of the sun, from our point of view.
The absolute edge.
So we took the full punch of the light speed radiation, but we dodged the cannonball.
That is the perfect analogy. The flare is the flashbulb. The cannonball is the coronal mass ejection, the CME.
The CME. That's the giant cloud of plasma and solar gunk that comes after.
And it travels so much slower, it can take 2, 3, even 4 days to get here.
So the light hits us instantly, causing the R3 blackout. but the big system-killing cloud is still days away.
And because the flare was on the sun's edge, on the limb, that cannonball, that CME, it was launched mostly sideways, away from us.
It missed.
Analysis confirmed it. The CME did not have a clear Earth-directed trajectory, so we got grazed by the light. But the physical material missed us completely. And that immediately eliminates the threat of a severe geomagnetic storm.
And that's where the other scale comes in, the G scale, the one that really measures the threat to our infrastructure on the ground.
Exactly. The G scale is based on the KP index, which only really spikes when a CME slams into our magnetic field and makes it rattle. Since the CME was fired sideways, the forecast for the next 3 days was G none.
Hold on. An X1.9 flare, one of the biggest we've seen, and the geomagnetic storm forecast is G none. That just sounds like we got incredibly lucky.
It's not so much luck as it is predictable geometry. If that exact same X1.9 eruption had happened in the center of the sun's disk, pointed right at us,
Oh, it'd be a totally different story.
a G none forecast would be impossible. We'd be bracing for a major G2, maybe even a G3 storm. Power grid managers would be on high alert everywhere.
That really puts it in perspective. Because we avoided that G-storm, we avoided all the things people really worry about.
All the big ones, the ones that cost billions. Power grids, for example, didn't have to worry about geomagnetically induced currents, or GICs.
Those are the currents that can flow through the power lines and actually melt transformers.
They can cause cascading blackouts. It's a huge threat. But with a G none forecast, they could just maintain normal operations. That saves a ton of money and resources.
And what about things like GPS?
Same story. GPS networks weren't subject to what's called ionospheric scintillation. That's when a G-storm messes with the atmosphere and seriously degrades GPS accuracy. So our navigation stayed precise.
So this event was almost like a perfect test case. We got the R3 shock, but without the G-storm that usually follows.
It was a very expensive, very informative cosmic fire drill.
Before we move on to what this all means for the future of Solar Cycle 25, let's take a quick moment.
If you appreciate us sorting through the noise and explaining why you didn't lose power, please hit that like button.
And subscribing ensures you never miss a deep dive into these stories that, well, they really do matter.
Okay, so this X1.9 flare wasn't just a one-off event. It's a sign of things to come.
It's a warning. It confirms that Solar Cycle 25 is fully engaged. It's near its peak. But even though the big CME missed us, the flare did reveal another separate threat.
We're talking about the S scale now, solar radiation storms.
Correct. The S scale tracks solar energetic particles, basically super-fast protons that get accelerated by the flare's initial shock wave. The forecast still had a 20% chance for an S1, a minor solar radiation storm.
So why should you, the listener, care about a minor radiation risk if we already dodged the big G storm? Who does this S1 storm actually affect?
Two main groups. First is high-altitude aviation.
The Earth's magnetic field is a good shield, but at the poles, it funnels particles down. So flights on polar routes, they're more exposed. An S1 storm means flight crews and passengers get a higher radiation dose, so airlines have to monitor that very closely.
And the second group?
Satellite operators. These high-energy protons, even at S1 levels, can get through satellite shielding.
And cause problems.
They can cause component failures, corrupt memory, all sorts of issues. So operators often have to put their satellites into a safe mode during these events to protect them.
So this single event was an R3 communications blackout, an S1 radiation advisory, and a G none infrastructure reprieve all at once.
It's complex, but I think the most unsettling part is the prognosis. What comes next? This eruption came from a brand new region, AR4299, that was just rotating into view.
It was just getting started.
And at the same time, there's another massive magnetically complex sunspot cluster, AR429496, that's also rotating onto the solar face.
So we have two ticking time bombs now pointed in our general direction?
It means we're entering a period of extremely heightened risk. The sun rotates about every 27 days. Both of these volatile regions are very likely to survive that rotation.
And they'll swing back around to face us.
They'll rotate right into the center of the solar disk, the Earth-facing side, in late December 2025 or early January 2026.
Okay. So if an X1.9, or maybe something even bigger, happens from that central location, from the bullseye, what changes?
Everything. That geometry guarantees the CME is aimed directly at Earth. An X-class flare from the central meridian would almost certainly mean a severe geo-effective CME. It would mean a major G-storm is on its way.
So this event wasn't just a near miss, it was a preview. It was a demonstration of what this solar region is capable of.
Exactly. Infrastructure managers saw the raw energy output. Now, they have to prepare for that same power being directed right at us. The clock is basically ticking down to the next rotation.
So to summarize this deep dive for you, that X1.9 flare was an instantaneous R3 punch. It knocked out high-frequency radio across Australia and Southeast Asia.
But Earth dodged the big one, the geomagnetic storm, because the flare happened on the edge of the sun. The plasma cloud went sideways, giving us a GNUN forecast and sparing our power grids and GPS.
However, the message from the sun is clear. We just saw what this active region can do. This was the test run. Now, critical infrastructure managers have to get ready for when that region is pointing directly at us at the turn of the year.
Preparation based on this advanced warning is really the only way to minimize what could be a huge impact from Solar Cycle 25's peak. We've seen the gunfire, now we just have to wait for the shooter to turn around.
Don't forget to hit subscribe so you can join us for our next deep dive.
Thank you for listening to Two Beans in a Pod.